Hi everyone, I am Dr. Sachidanand Sen, working in the Department of Tripoli, SR University, Warangal. So we are continuing with the battery management system, and we are on the ninth lecture today, and the topic will be circular economy and recycling of energy storage system. So what is the purpose of doing circular economy or recycling, so that we can use the precious metals or the components for the requirement in the batteries for the extended period of time, so that the battery need not be manufactured more frequently. Similarly, rare earth materials like lithium, iron, cobalt, some of them are hazardous also, should not be that much frequently extracted from the mining or that much frequently used to build new and new batteries. So as long as possible, we should be able to use them or recycle them, reuse them for extended period of time. So that is the overview of the lecture that we are going to see today. So first of all, introduction, the circular economy in energy system. So what is the meaning of this concept called circular economy? So it replaces the traditional idea like take, make and dispose. Okay, instead of that, now we are going for make, use, reuse. Okay, as long as possible we have to use, like first life of the battery in electric vehicles, then second life of the battery in the uh, stationary power systems, microgrid and all, then go for recycle, and if possible some of the components we can recover also. So this is the phenomena which involves circular economy. So completely, as long as possible, we should be able to use the battery for the extended period of time. So in energy storage systems, circular economy mainly focuses on the extending product life, okay, maximizing the material reuse. So multiple times I am saying reuse means again and again we have to use as long as it is working properly, as long as its capacity, its efficiency is not degraded below a certain level. So reducing the dependency on new resources. Okay. So linear model. So linear model means extraction will be there, manufacturing and use and waste. It will be thrown for landfilling and all, dumped into the ground. So circular model is, from there this term is coming. It is forming a circle. Okay, we will see lot of diagrams and features and all. So design, reuse, use, reuse, remanufacture, recycle back to the supply chain. So some of the components which can be recycled then again will be used in the process of or combined with the new materials to form something again. Okay, so that is the circular economy. So what is its importance? So global EV demand projected to be greater than 300 million EVs by 2030, which is requires massive lithium, cobalt and nickel consumption. Just now I was mentioning some rare earth materials are there. Some of them are hazardous, okay, chemically more problem for the dumping or ground dumping or water dumping. So they are not that much sustainable materials. Okay, so battery contributes greater than 30% of EV's carbon footprint if not recycled. So as from the beginning I am saying that even though people are considering electric vehicles to be green and clean energy source, because we are not using any crude oil and petrol and diesel which is not emitting any carbon dioxide, but the thing is the manufacturing process, extraction process, okay, that is the fact, they are the main problem in this carbon footprint, release of carbon footprint during the production stage. Operation phase electric vehicle is good enough, but during the production, if we are not able to use the battery properly after the first use, second life, like that, so it will be a problem. So circular economy enables resource recovery, waste minimization and sustainability compliances. Okay, so key statistics, some estimates around 2025 has been made that 11 million tons of spent batteries expected by 2030. So this much tons of batteries, where they will be thrown, where they will be dumped, or where it has to be reused, that is a big question mark. And only 10% of currently recycled efficiently. So from out of all the batteries that are going waste, only 10% we are able to recover, and remaining we are simply throwing them onto the grounds. Now gives the complete picture regarding the circular economy. So you can see a circle is being formed. So raw material is coming into this circle, then it will be going through the process of the manufacturing, that is design, production and remanufacturing, distribution, consumption, repair and reuse. Then again lastly it will be going for waste. Some of them will be of course again recycled and again will be matched with this one. So this kind of loop, a closed loop which is forming, is called the circular economy. So directly not making something useful to be as a waste. Okay. So something whichever is possible to be extracted even from the waste material, that need to be extracted, processed, okay, enriched, and then if possible they should be reused again and again, like that. This is the concept behind the circular economy. So same things are shown here: reform, design stage, reproduce, production and retransformation, reduce, okay, transportation, distribution, reuse, consumption, reuse and repair, collection, okay, then recycling, end of the life treatment, so like that. So this is all about the circular economy. Same things are also depicted here: direct recovery, indirect recovery, physical, chemical, biological, metallurgical, property classification, okay, then integration classification, how we can integrate this represents the battery recycling, okay, dismantling classification, property classification and integration classification. So there are different techniques of recycling that we are going to see now in a short time. So that is possible because of the circular economy. So this slide shows the stages of a battery life cycle. So first stage will be like raw material extraction, okay, then mining. In this process what happens? The mining of materials like lithium, nickel, cobalt, manganese, copper, graphite and all. So these are the important components that are required to be assembled to make the components of a battery: electrodes, okay, that connecting points, separator, electrolyte, then covering cell. All these things will be manufactured from these elements. Then manufacturing cathode, anode, electrolyte, fabrication and cell assembly. So these things are being done. Then in use phase what happens? Electric vehicles, we are giving highest priority in terms of battery management system. So there we are going for the best quality batteries. Then other usage are also there, like stationary storage, providing emergency backup supply and all. So that is possible. Then end of life means battery reaches 70 to 80% of the capacity. So if the battery is below 80%, that first life is over. We can go for second life. Okay, we can go for second life. So in that what happens? Second life we are going for stationary power system, power storage support and all. So second life used for stationary power system. Then recycle or recovery. So once that battery state will further degrade, okay, if it is now coming to 60%, 50% of the capacity, then for that stationary usage also that is not suitable, then definitely we need to dispose that or recycle the components. So whatever is possible to be recovered, we will recover, and the rest of the things will be gone as a waste. So materials re-enter the production loop when we are doing the recycling and recovery. So raw material, supply, manufacture, okay, sell, then use is there. So once manufacturing of the battery is done, then it will be sold to the customer or the EV car manufacturer. So it will be used here. Then collection, then repurposing, okay, second life cycle, some we can use. Then recycling, again it will be formed in the loop. Then something which we will not be able to recover, that will be thrown into the landfill, hazardous waste will be collected. So this is the complete cycle for circular economy. Same things are being also depicted here. So first use, okay, material recovery, and then mineral extraction, manufacturing, then battery production, use phase, okay, then car is EV is in use, then first phase, extended use phase. Okay, so this is the second life phase. So here you can see storage, urban e-mobility. Okay, some household solar panels can be integrated with that one. Then end of life, it will be coming to the recovery and recycling. Something will be extracted. Okay, spent lithium-ion batteries, some experimental extraction can be there, some waste landfill will be there. Again, otherwise recovered materials will be put back into the battery production loop. So this is how it works. So environmental impact. So what happens because of this large production reuse of the battery? So mining of 1 ton of lithium so consumes 19 lakh liters of water. It is based upon the brine extraction process. So 19 lakh liters of water. So cobalt mining linked to environmental and social concerns. So that is also a problem. Then recycling avoids up to 60 to 70% of carbon dioxide emissions. Plus finding virgin or new materials extraction. Okay. So material flows in a circular system. So how does the impact, how does it affect the environment? That we have learnt, lot of water consumption is there. Then cobalt mining will lead to environmental and social problem. Then carbon emission. So if we are making it possible to reuse some of the components, we are definitely helping reducing the carbon emissions, then water consumption and environmental pollution. Then what is the material flow in a circular system? So how this circular economy works, that part we'll see. Like raw materials are obtained, then manufacturing, battery is manufactured, then EV, electric vehicle, where we are using that one, then collection in that electric vehicle, that once that life is over, then it will go for collection and sorting. So not all the battery packs are equally damaged or equally old. So that sorting process is required to identify the newer and the older batteries. So those which were having less health, state of health is less than 80%, definitely selected for second life reuse. Okay, recycling. So material recovery will be there. Then back to supply chain. So that is the complete cycle. So circular systems create a closed loop supply chain. Okay, in supply chain, the components or the materials, raw materials are moving from one place to another. So this batteries, components, recycling, refurbishing, so all these things requires a closed loop supply chain, reducing the cost volatility as well as import dependency. So like most of the countries are depending on the rare earth material, they need to and which are available only in few countries. Like China, mostly lithium is available. So they are exporting to different countries. So that dependency is also creating lot of problem in foreign direct investment there, foreign exchange and all. So that dependency will also be reduced. Okay. So what we are doing here, the used battery, electric vehicle battery manufacturing. So here what we are learning, raw material and extraction. This is the starting point, we can say. So once the raw material and extraction and processing is already done, so what will happen, we will be going for the manufacturing. So battery will be created, then and means assembled in an electric vehicle. Then the used battery what we are getting, that can be either thrown through the junkyard, then or that battery can be refurbished. Okay, refurbishing company has to be collecting those old used batteries. Then if possible second life usage will be there. So reuse means pack are repurposed for a second life application in energy storage services that is suitable for their reduced performance capabilities. So whenever the battery was in operational for the electric vehicle, so when an EV battery can no longer meet its performance, then only it will be sent for the refurbishing, okay, or less than 80% state of health. So this is all about the first life and second life of the battery. Same things are depicted here: material extraction, manufacturing, exploitation phase, first use, then extended exploitation, second life. So here some algorithm need to be there to identify what is the state of health. If it is more than 80%, so it will be first life. If not, less than, then second life. So for second life also, how much extent it need to be extended? So greater than 75, greater than 70 or 60%. So depending upon the application, we are selecting the threshold values. Okay, so once it is done, end of life, then again it will be going for recycling and landfilling and all. So this is the complete cycle. Now steps in battery recycling. So what are the steps involved in battery recycling? So collection and transport. So as already mentioned, these are all part of the logistics, supply chain department. Okay, so safe logistics. So some United Nations, some compliance is there, how the transportation of the goods should be done properly without any emissions, any leakage or all. Then discharging, so neutralizing residual charge like anions and cations that will be available in the materials, batteries, they need to be nullified, their impact should be nullified. Dismantling, removing the modules and cells, that is also required as one of the recycling steps. Then lastly, material recovery. So extracting active materials, lithium, cobalt, nickel, copper and aluminium. So collecting and transportation, discharging, okay, nullifying the charge effect, then dismantling, breaking it down into from the battery pack to modules, from modules to individual cells, then material recovery. So all these processes are also done with the help of recycling processes. Already we have discussed all these things. Let us briefly again repeat that one. So pyrometallurgical means smelting of the batteries at high temperature. So it's like burning them. 1200 degrees Celsius smelting process is there. So cobalt, nickel, copper, all these things will be extracted. So this technique is highly matured, mature technique. High energy use. Okay, lithium losses will be there somewhat. Then hydrometallurgical. In hydrometallurgical, what happens? The chemical leaching is done with acidic materials like H2SO4. Okay. Then hydrogen sulfuric acid, then HCl, then here lithium, cobalt, then nickel, manganese and all. So high purity recovery. So because we are mixing chemicals or acidic medium, so all unwanted things will be dissolving in that. Okay, hydrochloric acid and H2SO4, they will be helping to dissolve that unwanted material, pure materials. Okay, that layers formed, SEI layers, that solid electrolyte interface, those layers will be also removed. So some form of cleansing will be done. So that is why we are getting high pure recovery. Okay, wastewater generation. Definitely some water is also required, so that will be wasted. So direct recycling, so physical separation we are doing, relithiation of the cathode. Okay, active materials, lithium, cobalt, O2. Okay, cobalt oxide we are getting, the nickel, manganese and cobalt will also receive. So retain cathode structure. So this helps to retain the cathode structure, requires clean feed and automation. So some form of extraction process is there which will be helping us to recycle the components. Okay, recycle the components from the battery individually so that they can be again reused in a better way after having some form of upgradation or refurbishing. Now process flows example, like briefly we'll discuss what is hydrometallurgical process. So shredding, okay, sieving and sorting, leaching, solvent extraction, precipitation, metal reuse in the cathode manufacturing. So these are the process, we have to break them down, okay, remove, leach them with the solvent, then we have to make it deep or precipitate it through the acidic solvents and water also. So recovery efficiency is lithium is around 80 to 90%, 85 to 90% will be recovered. Cobalt and nickel 95 to 98%, and copper and aluminum, which are metals, conducting materials, the 99% almost it can be recovered. So what are the companies that are involved? This is the briefly it is showing. In different countries are having different companies. Like in India, Etero is there, and almost this much tons, 11,000 tons they are able to extract. In Europe, in US we are having Redwood, then Umicore in Belgium is there, in Norway we are having Hydrovolt. So all these things are involved in some form of sustainable cleaning or extraction of the reused batteries for in a sustainable manner. So hydro based, zero waste recycling plant. So somehow they are able to reuse the first life cycle of the battery. Okay. Now same things are depicted again in a different manner. The direct recycling is there. So disassembly and material. Okay, depleted powder we can have, then burning them, then regenerated active material for new battery. Okay, so this is one of the methods. Similarly, pyro, we are again burning hazardous gases will be coming out. Then hydro based means some separation, acid leaching, precipitation will be there. Then biotechnology means some form of bio leaching will be using. Okay, so these are all process of recycling. Same things are also depicted in this slide. So pyrometallurgy means again that fire based, then hydro is there, biomaterial with lowest technology readiness. It is quite new and it is not yet that much developed. Okay, it is not yet evolved that much. So some form of battery retreatment, recycling are adding some value into the closed loop circular economy cycle. Okay. So same things are also again repeating. Direct method, pyrological, hydro, then in activation and comminution. Okay, separation is there, acid leaching is there, precipitation is there. So these are all the same repeated things again and again. These slides are there, so already mentioned, so I am skipping that one. So concepts of second life batteries. So now we will see where the battery can be used second life and what is the state of health range within which the second life which can be called to be an optimal way of utilizing the batteries. So EV batteries retire at 70 to 80% of state of health. Okay, still have usable capacity for less demanding application. So generally the first life is up to the 80% of the state of health. So once that period is over, we are going for second life. So in this range, it is highly suitable to use the battery for second life. So what are the different applications? Stationary energy storage for solar and wind system, already mentioned. Peak load management in microgrid. So if microgrid is there, if we are able to manage that peak load, means during evening time generally, generation within the microgrid is lesser and the demand is more. So if some energy storage devices are there, they will be acting as energy buffer, because during daytime when the generation was more, they will be able to store, the battery will be used to store the surplus generation, and during the evening time when the demand is more and generation is deficient, they will be able to supply the remaining gap. Okay, so backup power in the telecom towers or buildings. Okay, so Nissan and Eaton launches some X storage used in retired Nissan Leaf batteries for home storage. Up to 10 kilowatt modules of solar panel, they can be integrated with the solar panel modules. So again, same process of recycling. Okay, 3 stages are shown here. We will skip that one. Then what are the different aspects of recycling and where we need to check that one state of health, what is the remaining state of health. So suppose we are starting from battery manufacturing. Okay, here we will start and we are having a new battery pack, then scrap battery pack when it is state of health is less than 80%. So once that phase is over, we are going for the second life. So we have to estimate what is the battery's state of health presently. So if it is depleted battery, if less than 40%, we cannot use. If usable battery, if it is more than 45, if it is more than 40% means definitely we will go for battery repurposing and second life of the battery. And here again, once it is being used continuously, again it has to be cross-checked what is the present state of charge continuously, maybe within a gap of 6 months, 1 year, like that. So once that is working properly, more than 40% means continue to be sent for the second life, otherwise it will go for recycling. So this is the process involved for identifying the first life and second life based upon the criteria of state of health. So here also similar things are there. Second life, first life. components are defined here. So portable solar panels, okay, mountain side we are having, then grid stations, street lights, portable mini fans. So where we can use these batteries in the second life, that is what we are seeing. Electric bike, small generators we can use, solar and wind energy storage we can integrate, then cool flashlights with 9-volt battery. So these are some of the second life applications of the batteries. So technical challenges in the second life and repurposing of the batteries that we are having. Technical challenges, non-uniform degradation among the cells. So this is a major problem, that the cells are not degrading in a uniform way. Some of them will be working fine and some of them will be degraded drastically. So that identification is a problem. So that need to be clearly identified. They need to be sorted. Okay, they need to be separated and sorted. So non-uniform degradation among the cells, it creates a sorting challenge. The need for reconfiguration and new BMS. So based upon that, some of the old batteries which are not working properly, they need to be isolated. Okay, so if that configuration can be modified, okay, some new algorithms or new circuitry can be adjusted, so that this we can reuse the batteries or extend the good quality batteries or working batteries for a certain extended period of time. So regulatory and reliability issues are there, warranty and safety related things. Okay, the environmental and economic benefit, delays recycling needs by 5 to 10 years. So as much as possible, the recycling of the battery need to be delayed, so that the longevity of the battery will be more, and the requirement of newer battery, the demand of newer battery in the market will not be increasing. Otherwise, the manufacturer will go for making new batteries which requires fresh raw materials and all. So that will be again hampering the carbon footprint. It will be leaving a huge carbon footprint. Okay, so reduces the life cycle. So if we are extending the usage of the battery by 5 to 10 years, it reduces the life cycle CO2 footprint by up to 30 to 40%. So creates new market for the stationary storages. So as the life of the battery is extended in the second life itself, so for the complete stationary or the second life, we will never be depending upon the fresh batteries. So batteries will be only manufactured for the electric vehicles, and for the stationary storage or the second life, only the second hand batteries or the old batteries coming from the electric vehicles can be used. Okay, so that will definitely boost the concept of circular economy, and it will definitely help us to achieve the sustainability by reducing the carbon footprint. So I think same things are represented here. The first application monitoring is there, construction and packaging, first life, then first life usage, then second life. In that end of the first life, repair and repackaging will be done. Then usability, second useful life, like solar panel, battery bank is there and all. So identification and final destination like recycling or sending it for the dumping yard. Okay, so this is just brief overview of the recycling trends and first life and second life of the batteries. So here again same process I extended a little bit. So raw material, battery manufacturing, new battery, then battery state of health we are monitoring, and inspection and remanufacturing, repurposing and deployment. So if it is life cycle management and performance monitoring, until it is less than 80%, okay, it will be used for power supply, commercial bidding, utility grid and all. Okay, once it is again coming from here, renewable integration, industry, energy, smart grid, telecom backup, small vehicle transportation, emergency power supply. So all these are different applications in the second life cycle. Okay, emergency power supply, fast charging stations, transmission system support, stationary applications, automatic guided vehicles, telescopic handlers, okay, transport trolley, sweeper machine, that cleaning device which is inside the room, it will be roaming around, or in the railway platforms or airports, that cleaning machines are there, battery run. So there we can have this type of batteries, and until it is not 10%, 10% is quite low, at least up to 40% we can use these things. 40% of the state of health we will be able to use this. So these things are again similar things. So first, end of the first life, then we will be going into the recycling, characterization, transport and storage. Disassembly will be done, then here recycling, then repackaging. So it's like circular. At any point of time they can enter. Okay, any dismantling stage is there, whatever extracted components again can be sent into the market. Repackaging is done, it can be sent into the market. First life is over, then second life can be done. Okay, second life it can come from here for the second life. So like that a circular clear we can make. So here the yellow colors are showing the services, added values to the batteries and the components, whereas these blue colored arrow marks are showing commodity sold or used for recycling. So this is also a similar curve which I have also discussed in the previous lecture, where we have seen the first life is shown here. Suppose 100% of the battery capacity is there, it will be degraded up to 80%. So when it is 80%, we cannot use it for the electric cars or electric vehicle application. We have to go for second life application, that is stationary energy storage. So use for energy storage. So here we will start from 80% and maybe it is coming up to suppose 30%. So once it is going up to 30%, so first life is over, then second life is also over here. So beyond this point, it will be going for recycling, where it will be extracted. The important components, whatever materials are in good quality, they need to be extracted, and the remaining waste should be dumped into the landfills. Then, as already mentioned, different government, different worldwide, they are taking some actions. World leaders are taking lot of policy change and all. So in European Union 2023 battery regulation, mandatory recycling efficiency targets have been provided. Similarly, USA Department of Energy resale centers promoting direct recycling R&D and all. So EPR means extended producer responsibility for the electric vehicle battery. In China, they have given that when the battery is after completing its first life, the manufacturer itself is responsible to create the second life usage. Okay, they should help to recycle and refurbish those batteries. So that is their responsibility only. So in Japan also circular battery platforms by Toyota and Panasonic, they are used. So European Union, they are planning to recycling the goals by 2030. 95% of the cobalt, nickel and copper, 70% of the lithium, they are expecting to be recovery. Okay. Now coming to the India, so India also doing a lot in this domain. So battery waste management rules. So what are there, which was proposed in 2022, that is extended producer responsibility. Just now we have seen that it is the responsibility of the manufacturer of the battery itself. So how long they will be able to use that battery in continuity. Okay. So second life, first life, then recycling task, all these responsibilities are attached with the manufacturer itself. Then mandatory collection and recycling targets are also assigned. Then provision of landfilling of spent batteries. Then registration of recyclers with CPCB. Then FAME 2, Niti Aayog. So these government organizations, they are helping out promoting local recycling. Okay, they are building complete ecosystems, e-rickshaws. Okay, charging infrastructure. So lot more need to be done to be evolving this complete circular economy, especially in the developing nations like India. Lot of startups are also working, like Loham, Cleantech, Etero Recycling, pioneering the closed loop recycling. So in Indian, what are the challenges that we are facing is informal collection system. So there is no sophisticated complete system has been built. Okay, so it is informal. Okay, lack of advanced metallurgical facilities, so there is no proper recycling infrastructure also. So low consumer awareness, people are also not that much aware what is the importance of recycling, otherwise how much we are losing through this process. Then policy enforcement and safety standards, need strengthening. So from government sides also, lawmakers also, there need to be more policy need to be provided and safety standard need to be developed. So this is the some summary. Now we are coming towards the end of this circular economy and recycling of the energy storage systems. So to summarize the discussion, circular economy ensures stability through reuse, remanufacturing and recycling. Okay, so recycling, what happens? We are able to recover the critical materials, reduce emissions and stabilize the supply chain. Okay, so advanced recycling like hydro or direct methods achieves greater than 90% of the recovery efficiencies. Then second life applications provide an intermediate phase before recycling. So second life means at least 5 to 7 years we are able to extend the use of the batteries. So in India also lot of rules have been made, policies have been done in a major steps towards a national circular battery ecosystem. So with this we are completing this lecture number 9, where we have discussed about the circular economy concepts and recycling. So we will again meet in the next session. Thank you.